Okay, we continue to learn Chapter 3, Vector Spaces. Section 3, Linear Independence. Part 2, Linear Independence and Dependence. So first, we see the definition. The vectors v1, v2 till vn in a vector space V are said to be linearly independent if the homogeneous linear system C1v1 plus C2v2 plus till plus Cnvn equals 0 implies that the scalars C1, C2 till Cn must equals 0. Then we say v1, v2 till vn are linearly independent. And the definition for linearly dependent is like this. The vectors v1, v2 till vn must, in a vector space V, are said to be linearly dependent if there exist scalars c1, c2 till cn not all 0 such that this homogeneous linear system holds. So c1, v1 plus c2, v2 plus till plus cn, vn equals 0. Okay. If there are non-trivial choices of scalars for which the linear combination c1v1 plus c2v2 plus till plus cnvn equals the 0 vector, then v1, v2 till vn are linearly dependent. Since vi can be represented here, some vi can be represented as a linear combination of the others, then of course v1, v2 till vn they are linearly dependent. Okay. And if the only way the linear combination c1v1 plus c2v2 plus till plus cnvn can equal the 0 vector is for all the scalars c1, c2 till cn be 0, then v1, v2 till vn are linearly independent. So linearly independent means that none of v1, v2 till vn can be represented as a linear combination of the others. So every vector here is necessary. Okay. And now we consider linear independence and basis. A minimal spanning set v1, v2 till vn is called a basis for V. The first condition is any vector in V can be represented as a linear combination of v1, v2 till vn. This means this set is a spanning set of V. Okay, and also need to satisfy C2. None of v1, v2 till vn linearly depend on the other vectors. So this means every vector here is necessary. You cannot omit it. Okay, so a minimal spanning set corresponds to a basis for the given vector space V. Okay. Now we see some geometrical interpretation about linearly dependent and linearly independent. Okay, if x and y are linearly dependent in R2, then we consider here c1x plus c2y equals 0. We must have such a relation. For example, x can be written as a multiple of another vector y. If we assume c1 does not equal to 0. So from this figure, you can see that the vector x and the vector y, they are collinear. They are in the same direction or they are in the opposite direction. They are collinear. Okay, so in this case, x and y, they are linearly dependent. Okay, one can be written as a scalar times another vector. And if in this case, x and y, they are not collinear, okay, then you cannot write a vector as a multiple of another, then x and y, they are linearly dependent. So this case linear dependent, this case linearly independent. Okay. And in three-dimensional space, we can still see some geometrical interpretation. Okay. If the vectors x, y, and z, they are coplanar or collinear. Coplanar in the same plane, right? Coplanar or collinear, then they are linearly dependent. Okay. If the three vectors x, y, and z, they are not coplanar or collinear, they are linearly independent. If there are three vectors that are linearly independent, they can span the whole set. the whole space R3. Okay. Now, examples of linearly independence in R3. The question is that asks you to find which of the following collections of vectors are linearly independent in R3. We have this vector 1, 1, 1, 1, 1, 0, and 1, 0, 0. So in order to show whether these vectors are linearly dependent or linearly independent, you just check the linear combination equals 0, and you find whether there are non-trivial solutions or not. If there is non-trivial solution, they are linearly dependent. Otherwise, they are linearly independent. Okay, so to check whether they have a non-trivial solution or not, you just solve the homogeneous linear system. So these three vectors, in fact, they are linearly independent. You can check later. It should be C1 times this one plus C2 times this one equals 0. You can find what is C1, what is C2, right? You must have C2 equals 0 and C1 equals 0. So these two vectors are linearly independent. And also this one, you just also consider the homogeneous linear system as C1 times this vector plus C2 times this vector plus C3 times this vector equals 0. And you find if there's trivial solution or not. And in fact, for this one, it should have a non-trivial solution. So they are linearly dependent. Okay. See the first example. We just write this equation. C1 times this one plus C2 times this vector plus C3 times this vector equals 0, 0, 0. Then this is a homogeneous linear system where C1, C2, C3 are unknown variables. So you solve this one, and the only solution to this system is C1 equals C2 equals C3 equals 0. So the three vectors, they are linearly independent. Okay, the coefficient matrix is non-singular, you can find. This matrix is equivalent, row equivalent to identity matrix. It is a non-singular matrix. And for the second one, you also consider this linear combination equals 0 vector. So it is C1 times the first vector, 1, 0, 1, plus C2 times the second vector, 0, 1, 0 equals 0, 0, 0. And you consider this homogeneous linear system. And it is easy to find that the only way for this system holds is that C1 equals C2 equals 0. So this system has only the trivial solution. So these two vectors, they are linearly independent. Only the trivial solution refers to linearly independent. Okay. And for these three given vectors, we also consider this equation. C1 times the first vector plus C2 times the second vector plus C3 times the third vector equals 0, 0, 0. So you can transform it as this homogeneous linear system. The first column is 1 to 4, the second column is 2, 1, 3, and the third column is 4, minus 1, 1. Okay, this homogeneous linear system, you can find this matrix, coefficient matrix, is singular, and hence the system has a non-trivial solution. If we have non-trivial solution, this means the vectors are linearly dependent.